Okay, do your lab course. Okay, so yesterday we talked about Pauli spin matrices, right? And and today we would like to have some more intuitive idea about spin of a microscopic particle, right? And if we go back to that experiment, Stern-Gerlach experiment, what we had the atoms, right? And these atoms, they don't interact with anything, and then they interact with inhomogeneous magnetic field. So before interaction, what do you think about before interaction? If I assume electrons here, okay? For the sake of argument, if I assume electrons, electron is not interacting with any external field, then how can you describe that electron? You can describe that electron in terms of superposition. The electron is in some superposed state where all you have is those probabilities, right? You have all those probabilities, probability 1, probability 2, probability 3. You can have a long range of probabilities, clear? So, once it interacts, what happens? The wave function collapses. There is collapse of the wave function. And you come up with the probability. What is the probability for an electron to have spin up? What is the probability of an electron to have spin down? So if I start my argument from a state vector psi, okay, I take psi, right? And this psi is 1 by under root 2 spin up plus spin down. What does this equation tell us? This equation tells us that the spin of an electron is in superposition, right? Right? So it is in superposition, but I want to measure it. So if I want to measure it, I can calculate its probability. I can calculate the probability of measurement. Are you getting my point? Are you getting? Low. So, see, if I take spin up and I act it on psi, what will I get? I'll get 1 by under root 2. This 1 by under root 2, all of you know, it comes out of those normalizations, okay? So when you have those probabilities, you have done all of these things. So what you will get here, you will have spin up and spin up. Then plus, what you will have spin up and spin down. Could you understand this? Right? So you have operated the bra of spin up on this state vector psi, and you operate it on spin up in the superposition, and you operate it on spin down. Now, what is spin up equal to? Come on. Very good. This is equal to 1. This is your that normalization. And what about spin up and spin down?
0.
This is 0. So what will I get? Have you written it down? You have written it down? Come on, do it fast. So by the time you write, okay, so we have taken a superposed state of electron and we define it as 1 by under root 2. Then you have spin up and spin down. And then we act spin up state on this state vector, and we use orthonormality conditions. And what we obtain that this spin up on psi is, what is it? It is simply 1 by root 2, am I right? This is simply 1 by root 2. Now I can calculate the probability of spin up. I can calculate the probability that you will have the particles with spin up that we observed in Stern-Gerlach experiment. So we are trying to explain the results of Stern-Gerlach experiment using the quantum theory. Clear? Okay. So I can go on to the next page now. Okay. So if I say that P, this is my probability, this is probability of having, the probability of having spin up particle. So how do we define probability? We define probability as whole square. Clear? Fine? Okay, but we have already calculated this bracket. What was its value? We have already calculated this bracket. What was its value? Its value was 1 by root 2. Getting my point? So, probability of having spin up will be 1 by under root 2 whole square. The square root will go and you will get 1 by 2. This is what you observe. You have the half probability of the particles having spin up, right? And you can calculate that mathematically. You can calculate that theoretically. And we can do the same exercise for spin down. Have you written it down?
Yes, sir.
So we will do the same exercise for spin down. And what will we obtain? So we will have spin down acting on the state psi. That will give us 1 by root 2. Then spin down, and here you have spin up. And then plus spin down and spin down. Am I right? Clear? Now there is no problem in having the value for this equal to 0. There is no problem in having the value for this equal to 1. Right? So I will have spin down on the state psi equal to 1 by root 2. So I can write down the probability of having particles with spin down states. That will be given as spin down state psi whole square. Right? So this is simply 1 by root 2 whole square. This is equal to 1 by 2. Right? So the probability of having particles with spin up is half, and the probability of having spin down is equal to half. This is what we observe on Stern-Gerlach experiment, right? We see one portion of the detector being hit and another portion of the detector being hit, explaining the way that you have two outcomes, you have two possibilities, right? In fact, when this superposition is there, when you are not calculating, when you are not observing, when you are not measuring your system, the spin has infinite states. The spin it can have all probabilities involved in that. But once you make the measurement, you have the two states. You have probability of having particle with spin up and having a probability of spin down. Is this clear?
Yes.
Now we want to discuss another important problem, and that problem is we have this spin now, okay? We have spin. And what is spin? It's an intrinsic property of microscopic particles, right? How does it look like? We don't know. It has no geometry, right? And you have this spin, and you want to interact this spin with the magnetic field. What does that mean? That means there is no other interaction involved. There's no other interaction involved. Your problem is that you are applying magnetic field, and this magnetic field is rotational in nature, right? So we are acting on the spin of the particle, applying magnetic field which has rotating nature. Now, what is so strange about spin? If you talk about the classical domain, right? And if you have something, and this is the initial position of something, and you will rotate it, it will come back to its own position, right? After how much angle that's traversed by this object, it comes back to its original position?
2 pi.
It's 2 pi, 360 degrees. But spin, as I told you, it's a two-dimensional space, and it's a complex space. It's a complex space. So when you have a complex space, you don't have any geometrical interpretation of this space. Now, if you have a spin, and this spin rotates, the spin will reach its initial position only when it will traverse an angle equal to 720 degrees. This is the mathematical reality of the spin. I cannot describe it. Are you getting my point? The spin, starting from its initial position, if it has to reach back to its initial position, it has to cover an angle equal to 720 degrees.
4 pi.
Which is not the case. So it is not that intuitive geometrical thing that we are aware about. See, we are in some geometrical situation, right? And we understand x, y, and z, right? And if you have a rotation in an xy plane, you always understand that if your system is symmetrical, the point that's rotating by an angle equal to 360 degrees, in the same plane, it will reach back to its initial position. But that's not the case with the spin. Spin reaches back to its initial state when it traverses an angle equal to 720 degrees. Now, if you ask me a question how, it has only the abstract mathematical way of understanding that how it comes back to its original position by traversing an angle equal to 720 degrees, right? So this is our problem now. So what we have, what am I telling you? I'm telling you that I have an interaction of the spin with a rotating magnetic field. Rotating magnetic field. Rotating magnetic field. I think we will discuss this tomorrow, okay? If you have any questions, you ask me. Any question? Don't have any questions. Any question? Okay, thank you.